Everyone, thank you for being here today. It's my pleasure to introduce Dr. Abu Kibria. Kibria is a research associate in the Department of Fisheries and Wildlife here at Michigan State University, and also the Midwest Climate Adaptation Science Center. He is a research associate in my lab. I'm Angela Burrow, if you don't already know me. Prior to coming to MSU, Kibria was a research associate with the Southeastern Climate Adaptation Science Center at North Carolina State University. He completed his doctoral degree at the Australian National University with a specialization in ecological economics. He specializes in leveraging data science and econometric modeling to bridge the gap between complex environmental and societal challenges. His ability to leverage AI tools to generate meaning from extremely large volumes of literature has been indispensable in our project, where we are investigating critical knowledge and knowledge gaps around climate change resilience and restoration of Midwestern wetlands. Today, he's going to share a novel AI framework for doing this work and key insights from its use to conduct a scoping review on climate adaptation and wetland restoration.
Just a second. Excuse us. And this is the one. And this one. It's good to go. Yes, it's okay. Yes. The slide is not moving. It's moving here. Yes. Yeah, sure. It was moving there. So it's moving here. So maybe they shared the wrong slide. Maybe that one. Okay. It should work. It's moving here, so I guess the screen will be that one. Yeah, yeah. That one. Yeah. This one.
To share this.
Yeah.
Now it's to share this and your notes would be seen.
Okay.
Try now.
Yeah, no. So it's moving here.
What is it? This. You have to close this. Now, right?
Yeah. All right. Thank you, Angela. Thank you so much for coming this talk. And thank you for your patience from this initial technological hiccup. I'm going to talk about multi-agent AI architecture that we use for our synthesis research. So here is the breakdown of my talk. We'll understand some of the background about our research problem, a little bit about AI agents and agentic systems, and then what we are aiming to do with that system. And then we'll see the agentic architecture that we are using for our research. And then we'll present a case study where we implemented and deployed some of those architecture to analyze our existing data set. And so in that research, we will show some of the findings. And then finally, I'll discuss the scalability and transformation capacity of AI systems for our natural resource research. So this is our project. We aim to understand the critical knowledge gaps in climate change risk to wetlands and wetland ecosystem services in the Midwest region. As you know, that wetland is a unique ecosystem and provides many vital ecosystem services. But we have incomplete understanding of these vulnerable socio-ecological systems. I say they're vulnerable because we have a lot of pressure from environmental changes as well as anthropogenic activities. So to understand that one of the popular methods is to run a scoping review for the literature we have for our based on those ecosystems over the years. So if you don't know what is scoping review, it is a method to map the body of literature, identify the concepts, and also find out the research gaps in over the years of research on a particular field. So technically, this is a prior stage of determining the feasibility, whether we should do a systematic review or meta-analysis. So this will help us to identify those research gaps that we need to focus on in our meta-analysis. But the problem is that the exponential growth and its availability of our knowledge and research, it provides us a good opportunity to base our understanding on a very diverse knowledge base, but at the same time, it puts a huge challenge for us to analyze or understand from those large data sets. So technically, what we do, we limit our study within a certain temporal or spatial scale just to complete our research. But in our systematic or scoping reviews, there are several steps which takes many of our resources, but they don't contribute significantly to the creativity of the work. So we have large volume of data, but limited resources. And then we need to do a trade-offs to complete our research. We have graduation demand, we have postdoc as a limited fixed term position. So there are many factors that push us to reduce the effort we put for our research. But the agentic AI, it's a paradigm shift, complete shift from the existing limited research capability to revolutionize the analyzing the large volume of data. So if you look at the figure, it is just human involvement is only in one task. And the rest of the task, those agents can complete. So we can achieve incredible level of efficiency in terms of research we do. But to build those agents, it requires certain time and also effort and definitely human involvement. But at the same time, once it is developed, it can run on its own. So putting some time to develop that one, and then eventually we can benefit in the long run, and continuously we can utilize these framework. So history of AI is not something new. The tools we know, they are not new. Only the combination of those tools are new. So the mathematical functions, statistical, analytical tools, they all are there for hundreds of years. So it is considered the 1950, perhaps the initiation of AI in our research work and then industrial activities. But if you look at the chronology, the time between those major changes decreased over the years. And it is moving so fast that even people with understanding of those AI tools are struggling to keep up. So, but we only became very much aware on this after 2022 that AI is something. So what is the critical point there that we suddenly become very aware that AI is something, is revolutionizing the whole activities, workflow, whatever we say. So I will discuss that critical point for these changes in my subsequent slides. But if you look at this, this one is artificial intelligence is always been from 1950s. It is there, but then gradually it moved to different stages. So while I was working with a model for machine learning and then eventually deep learning model, we were technically utilizing one agent or one program at a time, and then efficiently completed one task or maybe one or two tasks. But the change happened when we developed this orchestration. So that helped to utilize those deep learning or other machine learning models to combinedly work together. So that orchestration changed everything for understanding those, for performing a complex task. Okay. So a little bit about AI agents. AI agents are automated goal-directed tasks. So we write the code for a specific task, which automatically it can perform some of those tasks. And then modern agents can perceive and reason and initiate actions. So this is the critical point that changed the understanding and application of AI, that perception and reasoning power. So that previously AI models were not able to do reasoning more efficiently than currently it is doing. So that helped to perform more like human-like activities in this workflow. And then it can automatically and dynamically work together and then take actions without any involvement of human being. So AI agents demonstrate a reactive intelligence and some level of adaptability. So where human does not need to be involved once we develop that architecture. And what is the agentic system? So it is a combination of agents together, that few agents work together to perform a complex task. So depending on the architecture, they can coordinate, communicate, and dynamically allocate resources, subtasks, and then perform a complete task. So there are many different tasks. It can be linear, it can be hierarchical. So there are different architecture we can utilize for our research. But there is no hard and fast rule in terms of how we organize our agents. It depends on the research or activity we intend to perform with this framework. So to come to my research is that our aim is to develop a novel framework of agentic system, AI agentic system that can complete the work and at the same time become compliant to the high standard MSU has for research and data privacy. And also in the process, we will continuously evaluate the efficiency and accuracy of AI agentic systems for our research performance. So here is our case study that where we try to understand the research gaps within the history of wetland restoration research in the Midwest region. So we have been working with our library, and this is the Boolean search string that we utilize for getting article list from the Web of Science and also the Scopus. So these are the two databases that we use to to find the reference materials that we will use to review in our research work. So we came to this point that we need to review about 16,802 articles. And this is humanly resource-wise impossible. But if we now go to reduce our scope and then go to, say, reach to 50 articles that we will review, which generally the practice, 50 to 100 articles, maybe 200, which is generally the practice. But the trade-offs here that we leave a lot of knowledge out of our consideration. And so that is the point that when I decided if we can utilize some of those tools, then we can understand much broader context of this research. And then I started to develop that AI architecture to analyze all of those research materials. So we are going through a rescreening and then data synthesis. That will be our next steps and findings and reporting, and then peer review articles and extension report for that. So in most of the work, we will utilize AI agents, but only the writing and then creative interpretation. That is where we will focus our energy. So that will make this research paper more creative than if we don't have much time to produce more creative materials. So that's what our aim is to achieve from this project. Okay, so first of all, any agentic system require to understand the design principles, because that is the case where we decide what will be the structure of our architecture. And once we develop that architecture, we have little, sometimes no chance to eventually change this to a new architecture. So this is the crucial step that we need to think about at the beginning. So we have developed a multi-agent system, and also project that is also modular in this framework. So why we went to that multi-agent and which is modular? Because as we know that our academic research is not always constant, and we as we go through the steps, our research question changes, our research plan changes, analytical framework changes. Many things, it happens over the research life cycle. So in that case, if we just develop follow one architecture that is from front to end, and we decide at our first stage, and then if we need to change, we wouldn't have much time to do that. So that is why we put this one as a modular. So in this modular architecture, one by one agents will be added into the architecture, and then it can communicate and coordinate this work. So that will help to follow the path of our research, that over the time we develop our research question and utilize different analytical tools. So this will help us to do addition and exclusion from our architecture. And is also emphasized on task decomposition and also extensibility. So some of them I already discussed. And then it is a static, sequential, and modular architecture. So static in a sense that we had to think about some of the limitations of utilizing AI tools, is that I'm just trying to utilize that one that we can run with our laptop. We don't need to go to a supercomputer to run that model. So in that case, in that architecture, once one agent completes its work, it shuts down its activity. So technically, it is not pushing too much energy consumption of my laptop. So gradually shutting down each of those will eventually makes only one agent is running on my computer. So that reduces the energy consumption from that system. And sequential is that every sequence saves output. That helps human to look at the output and then decide whether we should utilize further agents or not. But if we don't save that output, we don't sequential, we make it sequential, these agents are so smart that they can just take the data and perform the task. So in that case, what they are doing, we have no idea. So that is why we try to develop that each of those agents, after that, they save the output, and then our team looks at that. If there is any further revision we need, we do that after that. So in every steps, human is involved, and we see what's going on throughout the whole architecture. And then it also helps us to increase the scalability of the work. We can utilize 10 agents we can add into the architecture, and also transition to a more advanced level AI agentic system. So in our work, we have multiple models. Some models require a LLM involvement, some models don't. So we have the capacity within the architecture. If we want to transition to LLM models, we can transition into that. So these are the different principles that we need to follow before we design an architecture. And more importantly, maintain a human presence in the loop. So this HITL system helps us to always question the activity of agents. And that helps to understand that what is the agents are doing and how they should work. And if there is any requirement for human intervention, we can intervene along the process. And then the governance. So this is crucial for our research and also for any agentic architecture development, is that no matter how beautiful our model is, if it does not comply with the institutional policy, there is no use of it. So we need to be very careful in terms of how we design our architecture and how they will work in that system, how the data will be shared and utilized. But after even before, with the accountability and also the compliance, we also need to develop the trustworthiness of our model. If we are not transparent, if we don't have a governance framework in place, we will not be able to develop the trustworthiness outside our team, even within our team. So not all our team members are familiar with those language, but as soon as they see the architecture, we have a very structured governance framework in place, they can say that this is a reliable system that we can utilize for that. So the challenges of governance in agentic architecture is the data quality. So the quality data is very important in terms of how we run the model, and then security risk. So this is one of the key reasons that we need to think about AI system governance, is that these agents can work independently. Maybe that individual agent is compliant with the university policy or the institutional data policy, but when it collaborates with other agents, that agents might not be compliant. But moreover, when communication happens between agents, there is a chance that third-party involvement can be, or intervention can be possible if we use different models. So in that case, those kind of communication, how these agents are communicating each other, is also crucial to develop a very secure workflow. And then the sensitive data exposure, which is very important too. So it depends on what model we use. And so that will help us to decide whether we will share a certain data with that agent or not. So we can utilize architectural design where the sensitive data can be shared with some agents, and some agents will not have access to that. And sometimes we can share with the full architecture, sometimes only a part of the architecture. And as obviously, regulatory compliance is always an issue. It's very important when we do research. So these are the strategies that we are keeping in our consideration when we develop that research, is that agent permissions and boundaries. So even though there are some models which can perform its work, I'm putting some guardrails of that model, that how much they can work within the boundary. It is not able to work randomly or very independently within the data structure. So that helps me to push the model to do what actually I want, instead of just doing random within its capacity. And also the privacy by design, there is no point where we are in our team, we are compromising of our data privacy and the policy of the university. And data retention and lifecycle management policy, these are very common. We all maintain that. We are still maintaining in our research too. Transparency and explainability. So this is where it becomes a little bit difficult for this model, especially in the non-engineering disciplines. So how we explain those completely different coding language to a discipline which use different coding languages. So in my understanding is that we don't need to learn all the language, but we need to know what is the process. So if that process we are able to explain to people, they can give a very good feedback on that. So those are very critical too. This is my experience with my team to work with, that although our team has understanding about the wetland restoration and then a great level of knowledge on this research field, but at the same time, when they understood the process, they helped me to revise and fine-tune those models to a point when it became really efficient. So these are very important, that how we communicate that design architecture or the workflow to the people who are not familiar with that flow. And the data lineage and compliance assessments is important. Training, if we have to collaborate, that time a little bit training is also important, which at this point, we don't need much of that. And the monitoring and continuous improvement, that's what we are always doing, that every work we do, we go through the team meeting and discussion, and also all the process of critically vetting those activity, and then finally improving and fine-tuning the process. So this is the diagram that the workflow that we are using. The first one is the running the pipeline, where this is technically a window pops up when we run the model, and that will help us to start the run. And then this is the orchestration layer. So when we run that command communicates with the orchestration layer. Orchestration layer decides that which agents should be start working for the task we put on. So it then goes to the agent one. It goes to the data pipeline. So this data pipeline, in our case, it is the Zotero online library. So it goes to Zotero online library. I don't need to open any article or I don't need to even sign in to Zotero. It will go to the Zotero library, then find the articles, read those articles. Especially at this point, we are focusing on an abstract base because it's the first screening. So it can go to those 16,000 articles and then read the abstracts and then create the output. So in this output, it will collect the metadata and also develop a classification percentage, the similarity of under each of those themes. And then once the data is created, then the orchestration layer gets the message from that, and then it starts communicating to the next agent to work on the filtration process, and then it performs its activity and create the output for that. So all of those outputs, we our team members, we do analyze and see if that is working or not. So this is the way at this point we are working. So this is a very early stage of our development, and only 2 agents at this point we were able to build. So the first agent is, I mentioned that the categorization, and second one is the filtration based on threshold. So the first agent is the categorization. If you heard about the BART model, so this is an advanced level modification of BART model. So this model takes all the text and encode and go through the tokenization process, and then there is a transformer layer, which all those learning happens. So what happened is that every time we put in a text, it tokenizes all those texts and then create a vector data for each of those texts, and then eventually create the, how can I say that? So it characterizes all those tokens. And with all of those transformer layers, when it goes to the transformer layers, it shades some of the features, keep the important features, and then move forward. So there are several transformer layers it goes through, and then eventually pulled from the data set. So that helps to understand the meaning of the sentence. So previous models were only able to understand the context of a word, but this model can understand the sentence. So meaning of the sentence is important because people use words in different contexts, different terminologies are changed over when we write things. But understanding what is the meaning of this word within that sentence is the critical one when we find out the similarity, whether it is wetland restoration or not. So this is also a very important model, and some of those, they trained this model with over 1 billion billions of sentences to find out that accuracy. And they achieved accuracy. Some of them can be over 95%. Some they achieved 98% accuracy. So technically, this model understands the sentence, and then we can see that whether this paper is about wetland restoration or not. So that kind of classification we can do for other research topics as well. So this is the screenshot of the agentic architecture, I would say. This one is the pipeline run. So these are just a minimized version of those windows. So they are big pages for writing those codes. And then this is the orchestration layer where each of those agents are defined. So this one is one agent. It defines on that, and then gradually we can add more. So this one is our categorization agent, and this one is our filtration agent based on the threshold. And when we run that, it actually performs the whole workflow with that. So some outcomes that we have got from our work is that if you look, this is the left one is about comparisons between the model performance and a human evaluation. In terms of whether the article is based on it matches with the wetland restoration or not, and so it generated the cosine similarity. So the similarity between of theme and an abstract. We found that the human evaluation matches perfectly when the percentage match is 0. That's one approach. And then anything above 60% match, human evaluation matches perfectly. Within that, in between that, there are some level of disagreement between human and machine. So, and this model also prescribes that to make it more acceptable cosine similarity, the threshold is above 50% in some cases. So we ran this experiment with our team members, pulling from randomly 20 articles, but not 20, all of them are reviewed, but at least we had around 15 to 18 articles at this point, yeah. So from that random selection of articles from our 16,000 database, we ran this analysis, and then we decided that anything above 60% cosine similarity or maybe more, then we will consider that this paper is about that topic that we are looking for. And in the diagram B, here you see that in our experiment, we also asked our human experts that whether you agree with the percentage match of our articles for wetland restoration or not. And at the same time, they also prescribed that some of them are false positive in the sense that it should not be within that medium match. It should be low match. So the low cosine similarity is less than less than 40%. So the 40 to 60% is the medium level, and above 60% is cosine similarity score we consider as the high. If you look at these on the large circle within that node, is that where human agrees with that, yeah, this is the low priority, and this is high priority, and then this medium priority. But if you look at the arrow here, these are the points where humans see that machine identified it is medium score, medium match, but human consider that it should be low match. But interestingly, we find that only within that medium match, human also identified that this should be low match, but none of them within that low match and high match move to other categories. So it again proves the point that there is a certain criteria and threshold where after which the model performs perfectly with human evaluation too. And so the third picture graph also proves that within the 40 to 60% category, the precision level is very low. So before running those kind of cosine similarity analysis and then finding a percentage match of an article, we need to go through this threshold category selection where we can identify that up to which point we can utilize this model or not. So this one is the efficiency of evaluation. This is not a technically human and machine evaluation, but this is only for that task. So in terms of latency cost, the human took around 30 minutes to do that, to identify, read the abstract and say that, yeah, this is the wetland restoration paper and this is not. But the machine only took 0.4 seconds. It's less than half second. So that kind of efficiency is possible. And interestingly, this all happened in my computer within the laptop. So that we can easily utilize these tools for our research. Okay, so the human agentic system that we now propose for our research, we will be developing this one more. Is the orchestration layer where you decide all those design and the governance and everything, how the agents should work. And then we introduce that it's not like blindly agents are working. We introduce the human decision will be a crucial part and integral part of this system. So where every agent is responsible to go through the human evaluation. And then the output also, once the output is approved by the human evaluation, it will be taken as a final output. Otherwise, it goes to further revision for that. So in a very simple term, this is just another architecture with a HHGL system. So now it is the point that where how we can scale that for our research, even if someone wants to utilize this tool. Say, right now we are focusing on climate adaptation and wetland restoration. So the more keywords we use here, the more power it becomes. When diversity of working capacity of this model will be much more broader. But if someone wants to utilize, say, silviculture and climate adaptation, remove all of these words, write only silviculture and climate adaptation. Rest of the code will be the same. And then a silviculture researcher can utilize this one and benefit from the system. It will require only 2 to 3 minutes to convert it to a very different agent. So once one agent is developed, the whole department can benefit from it with little 4 or 5 minutes of modification. So it can utilize, I call it horizontal scalability. And so our one is that we can add more theme and identify the articles for our research. And the third one, another one, I call it vertical. So here, screening and filtration, that's what already graduated through our system. So now we are moving to data collection, agent development, and then the subsequent one. And then data wrangling, analysis, and visualization. So each of those are modular. So if someone finds this one, screening and data collection will be different. Say, if someone wants to utilize a microbiological data collection agent, they can just pull it off and then add an agent into that system. Then eventually it will work for the microbiology work. So in terms of analysis, is that hypothesis testing and then modeling and trend analysis. There is no limit. We can develop those agents and we can utilize those agents for data analysis and visualization. So keeping all those architecture and only that if we change the agent into that, it can perform the very different activity for our research too. So technically, with 1 or 2 agents, each of those laboratory can develop their own agent, data analytical agent, and then perform that work without changing other part of this architecture. And you only need to add this code, this type of code. This is just one code to add a new agent. So once the agent is developed, this type of code will be added into the orchestration layer, and then the whole workflow will work for that work. So you can gradually improve the whole architecture to work with that for our lab research. So how the transformation can happen? As you already know, that review works is a enormous amount of literature and work required. In that case, AI systems can reduce some of those intellectual burden on us and improve the research creativity. And also the routine works, which is very good at, these agents are very good at to automate those routine activities, data wrangling. Completely we can utilize those agents and then remove humans, significantly from that process, which sometimes are not very useful in terms of creativity. And the data analysis and modeling, we always do data analysis. Every time we bring someone, we start from the beginning and then run those analyses. But if we can develop agents into that for Hanover or modeling or trend analysis, that can be just plugged into the system without any training or modification needed. Some level of modification is important, but most of the cases we can utilize those tools and then save some resources for our research. And then obviously decision support and policy recommendations is also important, but at the same time, it improves the collaboration because of its scalability across the both horizontal and vertical. So I will be very quick, almost done. So utilization of AI system in natural resource research, how we can utilize. The biggest challenge is the lack of awareness and knowledge on our AI on these new tools, and also environmental footprint of those models. So what is the consequence of lack of awareness? Because in most of the cases, we don't have negotiating items when you go through the compliance and the privacy policy of utilizing all those tools, because we don't know how we are going to utilize those and what we will utilize. So that is why we always rely on IT people decides a policy for natural resources people, that how we utilize those tools and models. But if we go for an NSF grant negotiation, IT people don't decide that. We decide how we will, what items we need to perform those NSF grant application and then operate and perform all those researches. So it's really very important that what we are negotiating for, we need to, for that purpose, we need to understand that what we will use and how we will use those tools. But at the same time, I strongly believe that we need to develop a habit of mindset to move between the disciplines to create solutions. So instead of denying the capacity of certain research, we can embrace some of those research and then understand that how we can utilize those tools for our research. So when we face any trouble or problem in terms of research, we think within our discipline, but in some cases, there are many other disciplinary work. They perform the similar type of work with more efficiency and high accuracy. So if we can embrace those tools, we will be benefiting from these systems. But when it comes to the environmental footprint, this is already in discussion that whether this AI should be utilized in research or not. But I would like to start from this story about the environmental footprint in terms of utilizing AI. So this is a famous picture. We know that Gary Kasparov is playing a Deep Blue, IBM Deep Blue model for chess game. This computer can analyze, evaluate, do evaluation of 100 million moves per second. But yet, Garry Kasparov was able to defeat that efficiency. But they improved in 1997, had a rematch on that. You can easily understand that they improved because the screen changed. But the power is that it can now evaluate 200 million moves per second. And in that match, this is the first time Garry Kasparov in his career walked away from a game because he was not able to understand how it is playing. So he mentioned that if we can codify it and pass it to the computers, they will do better. But even he mentioned that in certain kinds of positions, it sees so deeply that it plays like a god. So he admits that this is a very efficient and accurate model, and we can utilize some of those resources. But there's another grandmaster, Suzanne Holger, said that you can go a lot further by just having a good understanding of tactics and then have only basic understanding of strategy. That is the point that I talked in my second slide, where, not the second slide, but the history of our AI, I mentioned that strategic understanding, the strategy within the tactic differentiated human to machine. Because the strategy is developed with our everyday interaction with our society and environment. Machine can do tactically impressive work, but it was not able to develop the strategic understanding. But that has changed when we developed large language models. So yes, these are very efficient. And also large language models are very energy and resource hungry models. But in this recent paper, they mentioned that if we carefully select models, we can reduce the energy consumption by 1% to 98%. So just only with that model selection, the energy consumption can be reduced overall across the world is 27%, which is equivalent to 5 nuclear power plants output. So technically, we can utilize AI with less energy if we select carefully what we are going to do. So in conclusion, I would say that we can significantly boost our research efficiency and productivity with AI, and also make collaboration easier and efficient in terms of data and analysis. But more importantly, by using small models to take the heavy lifting and then only calling the large models when things get complicated. So technically, we don't need to ask a general genius to handle everything. We can perform majority of the work, and when those models are not capable, we can ask for the other models. And then the true benefits obviously will come to our natural resources if we have better understanding of those tools and techniques and the knowledge base within our domain expertise. So this is our team that we worked to develop this model. And I'm very thankful that they provided very fruitful feedback for our research. And I'm also thankful to Dr. Dana Infante and Dr. Rich Kobe. I was just solving my problem in my cubicle, but you both saw the big picture on that. And thank you very much. And I also am very thankful to Dr. Akihiro Koyama and rest of the team. And lastly, I'm grateful that the USGS Midwest CASC for funding my research, and obviously MSU FW for supporting and providing all those logistic support for my research. Thank you all for coming today, and I'm happy to take any questions if you have.
So I think the architecture, the orchestration of the agents that we saw largely involved the categorization of those, say, 14,000 articles, and was answering yes or no with a degree of certainty whether they fit into those categories. What happens after you filter out the non-matches? Like, you still have 7,000 or 5,000 articles, and then what happens from there?
Okay. So it's not yes or no. It is a cosine similarity. So what happened is that it understands the distance between the words and themes. So there is a theme we are now currently demonstrating with the wetland restoration. It identifies whether how much close is the distance. So when we go to filtration process, we already have the data for 14,000, 16,000, over 60,000 articles. So the rest of the data, rest of the articles are not considered for our further step. So, but still, the analysis and the output holds those. If we want to revisit all of those, we can revisit that. So gradually, we are reducing to an amount that if that paper is wetland restoration, only those paper will be considered. And then we develop further research question to extract data from those articles.
So do you develop another agent at that point to take it to the next step, or is the final, you get to a point where then the human is doing the traditional synthesis, synthesis and creation of the categories or themes for the review?
So our target is to reduce human involvement with all of those works to the minimum, and then employ human resources for more like writing, analyzing, interpretation, and then creation of those articles. And along the process, we develop research question and to understand, to identify, to fetch data from those articles that we human do manually. We develop agent to do that. So gradually we will improve our architecture, and then we will answer the questions that we develop along the process. Well, when it comes to environmental footprint, it's also keep in mind that what is the net footprint? If I give 16,000 articles to review to students or PhD grad students or postdocs, we need maybe, I don't know how many, 50, maybe 100. Each of those will work. You need a space, you need a computer, you need lights, energy, and food. Just think that how much energy you save with all of this only with that model. So the net contribution is an important aspect for when it comes to footprint. But unavoidable, I don't know about any unavoidable risk footprint. As we know that it requires, if we utilize LLM models, it requires large data center to hold those models. And that is the case. Water resource and energy is an issue, but I'm not quite sure about the unavoidable constant costs for that at this point.
One more.
Yeah.
Bringing it back to your slide with the yellow table that compared the machine learning team and involvement, it said that on the human side, it would take maybe few researchers with 5 years of experience, and on the machine side, it takes no experience because it's a machine. How do you think that this will impact, considering scalability, how do you think it will impact human knowledge? Like people maybe not wanting to get PhDs if it's that easy to implement machine learning or AI with your research. Like, is that a concern?
To my understanding, that research will be very different in few years. That's for sure. But how fast it will be, it will depend on how fast we can adopt those technologies. And we will not think same way maybe 10 years down the line. So that'll be very different. So I would say the research will be very different.
Thank you so much. Thank you so much for coming over. Maybe if you sign up for that brief move to